Say again, Josh. This is mercury, right? Millimeters of mercury. But we're talking about hydrogen gas, right? So I see millimeters of mercury, but that's the unit. But what variable does that describe? Pressure, right? As long as you notice that unit is millimeters of mercury, that is a unit of pressure. So you immediately see a pressure is 700 millimeters of mercury. What else do you see? Label your, this is us writing our givens down, okay? Do this with me. What else do you see? Okay, so we see a volume, and that's not just any volume, that's the volume associated with this pressure, right? So we're establishing scenario one. Scenario one has hydrogen gas at that pressure and that volume. Those go together. I'm going to call those P1 and V1. That scenario, those two pieces of data describe the same scenario. Okay, then it's like, okay, scenario change. If the pressure is decreased, so I see another pressure at 538 millimeters of mercury. If the pressure is decreased, what will the new volume be? What is my question asking? Volume at this pressure, which is I'm going to call volume 2. Right, so this is P2, this is V2. Okay, so at this point we've only really learned one gas law, but you can imagine in the future you've got 5 or 6 in your head. You're like, okay, which gas law is it that has P and V in it? Whose gas law is it? Boyle's law. Okay, so these together make Boyle's law. P1 V1 equals P2 V2. Which variable are we solving for? V2. I never plug in values first because somebody's bound to put a value in maybe the wrong spot or maybe forget a decimal, so I always wait to do the very end, that way I don't have any butterfingers on this, right? So how do I solve for V2? How do I isolate V2? Okay, so I hear divide by pressure 2, and that's on both sides, right? So I'm just rearranging my equation to solve for V2. This I don't think is new to you guys at all. So V2 is isolated, P1, V1 over P2 is my new format of Boyle's law. And then I can do what? Plug it in. Okay, so 700 millimeters of mercury. I'm going to not squeeze this in this little space. I don't want to give you false hope that you can't write units. Okay, you must write units. So we have 700 millimeters of mercury. Write that down for yourself. Times, what's your volume 1? 500 milliliters. You actually do not in this case, because I'm not specifying my volume must be in liters. I'm just saying volume. So if I don't tell you, you get to kind of go with the flow. Okay? And then what goes on bottom? 538. Do not calculate yet. Let's think logically first, and then we'll calculate. All right, guys. We see the pressures decreasing, right? Should our volume go up or down? So here's your box of air. Decrease your pressure. Relax it, the volume gets bigger, right? That logically makes sense. So your volume should be bigger. If you want to make a note for yourself there, it should be bigger. That will help you doubly confirm that your answer is right, that you didn't type in something silly in your calculator. Go ahead and calculate. If you need to use your phone for now, I understand, because the calculators over here never end. But let's go. I need some calculations. Shout it out when you're there. I heard 650. This is what I remember. Point. Okay, I'm gonna go like that. That's what I'm hearing. And then we need to reflect and go, how many sig figs should this have? 3. These are decimals. That means there's 3 sig figs, 3 sig figs, 3 sig figs. This should be 651 milliliters. And did the volume increase from 500? Yep, it sure did. So, what were our steps? If you are a person like that loves having some steps to do some problems, I got you. What was our first step for that process? Givens, thank you. Givens written down, and then we figure out the what?
Questions.
Well, the question is kind of, I'm going to call that part of the givens. But then what do we do? Well, we had to identify the formula, right? It wasn't just like given to us. We had to identify which formula was applicable to this situation. I'm going to say ID formula. or gas law, however you want to say it. And then we rearranged to solve for the question. And then we plugged in values. Before we plugged in values, we talked to ourselves, right? It's not a sign of being crazy. It means you're intelligent. You're going, okay, let's rationalize this with myself. The volume should get bigger, and then you plugged it in, and you're like, okay, yeah, the volume got bigger, so I'm good here. All right, so that's Boyle's law for you. Let's do Charles's law next. I'm going back to my slides with the gas laws. Okay, so Charles went to Virginia Tech. Anybody think about what variables that would stand for? Volume and temperature. Volume and temperature relationship is what this one is going to show us. And before we learn the actual law, and we wrote it down, but I want to see if this makes sense to you. 1 second. Ooh, V, I see what she's saying. V and V. V and T. Okay, so do you think that increasing and decreasing my volume changes the temperature? Or do you think that temperature changes my volume? Temperature is likely going to change my volume. So, and I'll tell you why in just a moment. What constants would exist with this relationship, with these two variables changing? Hold on. What are the constant variables that you don't see up here? Okay, so at constant pressure and moles, where N is moles. Okay, so think about that. If I have a little box of air and I increase my temperature, what are the particles then going to do if I increase my temperature? They are going to speed up. So here's my thought process. Increase temperature, those things speed up. If they speed up, what are they doing with the container walls? They are colliding like crazy, right? So the collisions increase, right? And then you guys maybe saw in your reading guide and in your problem set 13, what do the collisions of the container wall do? They cause pressure, right? I don't know who said that over here, but that is the only thing that causes pressure, right? So increasing collisions causes the pressure to increase, and you're like, uh-oh, I said pressure has to be constant. So how do you combat an increased pressure? I can't change my moles. But what can I change? The volume, right? So if my pressure is increasing, you're like, no, what do you have to do to the box? Make it bigger. Okay, so essentially, an increased temperature, it causes all this little domino effect where the particles speed up, they collide, they cause pressure to increase. You're like, no, increase the volume really quickly so the pressure doesn't change. So that's going to cause our volume to have to increase so that we don't allow the pressure to change. That's the reasoning behind it. If you're interested in that, write that down. I think it makes logical sense, but if you're just like, I want to memorize the formula and lo and be done, the formula is V1 over T1 is equal to V2 over T2. So this is a scenario like our crush the can where I changed my temperature over time, and that caused the volume of our gases to change as well, and I can solve for a variable that wouldn't be given. So this one is temperature and volume directly or indirectly related? Say again? Directly related. Okay, so let's do a problem related to that. Go to number 6. Go to number 6 on your sheet that's in front of you. You want to stand up? Or there. Or you can sit here or you can go back in. Either way works. All right, so on number 6, tell me what you're seeing that's important. Okay, so a sample of carbon dioxide has a volume of, okay, so what variable is that? V. Okay, so V is 100 milliliters. And at what temperature does that exist? So that's our T, 273. Identifying the variables isn't hard if you know your units associated with the variables. Okay, then it says what volume, so what am I writing here? What volume, so this is actually, okay, so now I'm in a different scenario. I'm at V2. Okay, so these are V1, T1, and V2 is my question, and what's my other point of data? will occupy, so what volume of gas will occupy 300, what volume of gas will this occupy at 300 Kelvin? All right, so the gas law snaps you in the face. Who is it here? Charles's law, which I know we're doing this sequentially, but you should be able to identify. These are V and T relationship. What's Charles's law again? Okay, and we've written our givens. We've identified our law. We're solving for which variable? So I need to get V2 by itself. How do I get V2 isolated? Multiply by T2. Like I said, I don't think I'm teaching math to you. I think we're just reviewing this, but if you need some help with the math, let me know later. So T2 is going to cancel. Then this comes together over here. V2 is equal to what combination of variables? T2 times V1 over, see, T2's on top, right? Okay, so T2 times V1 over T1. Plug it in, and what am I writing?
100 times 300.
100 what?
Or 100 milliliters.
Okay, so I'm going to put V1 in first, okay. So 100 milliliters times 300 Kelvin divided by 273 Kelvin. What units cancel? I did not cancel units in the last one, but I would expect that you did probably. Kelvins will cancel. What's the only unit left? Milliliters. As long as that unit matches our variable, that means you did it right, right? Because if it was like Kelvin, you were like, well, volume can't be with Kelvin. That means you wrote something incorrectly. But we're doing good here. Before you type in your calculator, let's do a quick mind check here. What happened to my temperature? It what? It increased from scenario 1 to scenario 2. So hence, knowing our relationship, what should happen to our volume? Were V and T directly or indirectly related? Directly. So if one note goes up, the other one has to go up as well. So this should be higher than 100. Does anybody have an answer?
110.
It's one what?
100. But with 6 figs.
Fine, tell me before rounding. Thanks. I like to have my pre-rounded answer and then my after-rounded answer, so you can see the process of sig figs. So yeah, 3 sig figs applies all the way. That should be 110 point. Yeah, with a decimal. And that's going to be because I need 3 sig figs there. So far, so good, guys? Give me your thoughts. It's an algebra-based unit, right? We will have a little stoichiometry later, but it's going to be mostly this for the first couple days. Let's go back and do actually 2 more laws. And I may not do an example with this one. So going the right way, going the wrong way. Sorry. I was like actually in the right place. Okay, Gay-Lussac's law. Oh no, sorry, forgot Avogadro. Avogadro's law is not one that we use all the time. We use these other ones much more, but it does help to know that relationship. So Avogadro's law is a relationship between N and V. Tell me what you think about that. If I have a box and I have 1 mole of gas in it, let's just say it's 1 liter. 1 box, 1 mole of gas, 1 liter. If I pump another mole of gas in there, what do you think is going to happen? It's going to have to expand, because we didn't write it down yet, but what variable must remain constant if these are the only 2 changes? Pressure and temperature. And if I pump another mole of gas in there, what's immediately going to happen to pressure unless I expand? It's going to have to, it would increase because it's going to be colliding more with the container wall, the pressure would increase. So this is, N and V are related at constant pressure and temperature. And this one being, you kind of said this to yourself, increasing the moles cause what to happen to volume? Increase, so that's a direct relationship. So for yourself to understand, I think it makes sense to understand that the relationships cause the formulas to be written differently. So an indirect relationship, they're right next to each other, because as one goes up, one goes down. They kind of go back and forth. But a direct relationship, they're always written on top of each other like this. So if this is a direct relationship, which format is it going to take on? The bottom one. So it's going to take on a one like this. N1 over V1 equals N2 over V2. That is Avogadro's law. I'm not going to do one of those just right now, though. I'm going to hold off. And I got 2 more for you. one new one and then the other one to combine. All right, so Gay-Lussac's law. What variables have we not put in the formula yet? Together. So moles. Let's ignore moles for a minute because it's not going to be used a lot.
So is that an example?
We're not going to do one. Pressure and temperature. Right. We've done volume and temperature, volume and pressure, and we haven't done pressure and temperature yet. Right. So Gay-Lussac's is pressure and temperature with what remaining constant. Okay, so at constant moles and volume. Okay, so talk to me on logic. Is my temperature going to increase my pressure, or is my pressure going to increase my temperature? Who do you think causes what? Temperature definitely is the independent variable, whereas pressure is going to be the aftermath, the effect. So if I increase temperature, what's going to happen to my particles?
Faster.
They have more kinetic energy, so they start speeding up. So if they speed up, what do they do to contain their wall? Collide. And collide, increase number of collisions does what to pressure? Increase pressure. So you can see that they are indirect or direct? Direct. So I think that the little logic scheme maybe helps you understand what's happening. Or you can just memorize the formula, which is not always my favorite, but it's going to work. P1 over T1 equals P2 over T2. Again, that is how our direct ones are always written as a fraction like that. It's related to the infant variable. Generally. Mm-hmm. Okay, so if I asked you to combine Boyle's, Charles, and Gay-Lussac's, think about how that could combine. Look at the ones on your paper and tell me a new formula that would combine all of those variables. Anybody got a guess for me? Go for it, Jake.
P1 times V1 over T1.
Okay, hold on, pause there. So he said P1 and V1. Whose law is that? That's Boyle's, right? And then you said over T1. Okay, pause. If I cover up the V, whose law is that? Gay-Lussac's. If I cover up the P, whose law is that? Charles. So you see how they're all there together? It's just they're coexisting together, right? Okay. And I'm guessing you're going to say, great. Okay. So that is the combined gas law. And what you can do is you can resort to only using this, but at the same time, you have to understand which variables are constant. So if I go, oh, I got my balloon, and it's 1 liter, and I'm at negative 100 degrees Celsius, and then I travel, and I'm now at 200 degrees Celsius. What's the new volume of my balloon? What unit was never even mentioned? Pressure. So you would just erase that from the formula, and you'd have Charles' law. You see what I'm saying? If that variable is not mentioned, you just disregard it. But that's only if you want to use only combined gas law for these variables. And I'm a fan of using each of them independently. Do whatever floats your boat. Okay. If you heard me never say pressure in that example I just gave, that's because pressure is remaining constant. And that's because, so if it's not moving, it's not changing, I just kind of take it out of the system. Right, so at this, yeah, you would have to listen closely or read the question closely, because if it did have an amount, it would be a totally different law we haven't even learned yet, but this would be at constant moles. Right, good point, Joey. All right, let's pause for a minute. We have 30 minutes left. Let's go ahead and practice one or two more. You guys are doing 1 through 16 on this paper. 1 through 16. So you guys tell me. Do you want to start by yourself? Or you want me to do another one with you? Okay, let's do a combined gas one. If you want to start, you can start with yourself. Let's do number 13. 13. So, Megan, your paper? Will someone throw her paper?
I was writing.
Okay, so you guys write down the variables in number 13.
You can start.
Write down your variables. Good luck on that computer.
What?
Log onto your computer.
Oh.
A great chemistry teacher? What? Superior lab skills? 250 milliliters, which of those is an important variable? Hopefully the superior lab skills, okay. So, because it's a dangerous gas, alright, so this information is what for me? Volume, you should recognize milliliters as volume. Dangerous hydrogen chloride gas at 27 Celsius and 0.987 atmospheres. Looking at these units, you should be able to tell me the variables they represent. What variables? Temperature and pressure. Okay, what's already stuck out like a sore thumb? That darn Celsius. I'm going to give you Celsius every time. I'm that person. But you shall not use Celsius. You have to always convert to. So what's that in Kelvin? 300. Okay, so that's 300 Kelvin. And then we read more. When recording her data, she has to adjust her volume to STP conditions. That doesn't look like anything, but it is something. What is STP conditions? Okay, I hear 1 atmosphere, and I hear... Okay, I first heard 0, which then you said, okay, let's go ahead and make that Kelvin. So that's 273 Kelvin. What are these? What are these variables? Pressure and temperature. Okay, so now that I'm starting to see double variables, I'm going to go ahead and say the first ones that were all given lumped together, those are 1, 1, 1. And that these secondary conditions that are being given are 2, 2. And then the question here is, what's the volume that should be reported, right? So V2. So, as you're looking, identify the gas law. Combined gas law. Now, these headings do obviously help in the combined gas law section. But in the future, you won't see those like that. Okay. Oops. So this is like this floppy dot chop or cross multiply divide or however you guys pull the variable out. Which variable are we solving for? Volume. So how do I get V2 by itself? Okay, so multiply by T2 on both sides, and I heard divide by P2. I'm just going to kind of notate that like that, but I know where these variables are going to go. P1, V1, what else goes on top? T2, because that multiplication there, divided by P2 and T1 on the bottom. So we're rearranging variables. If you need some help with this math, I'll be a math teacher on the side here. So this is a B2. Okay. You plug, plug, plug. What variable should not cancel? Volume is, yes, I'm sorry, what unit should not cancel? Milliliters, right. And so P1 is 0.987 atmospheres. Oh, note to self. I knew that you guys said this is 1 atmosphere. If my pressure here had been like 700 milliliters of mercury, the atmospheres and the millimeters of mercury would not have matched, right? So we need to convert to one consistent unit of pressure. Whatever you pick, it will work, but just note that you can't use different pressures in the same problem. What's my V1? Okay, 250 milliliters. T2 is 273, and P2 1 atmosphere. T1 300 Kelvin. All right, so then you absolutely should be able to see the pressure unit cancels, the Kelvin unit cancels, and milliliters is the only unit left. So that helps you process your units that should be there. And what do you guys get? Anybody? 225? And you would then do what with that though? So yeah, you would sig it, but this right here is 0.00, by the way. Usually the constants don't limit you. That's 1.00 if you're confused. So you're like, well, there's only one sig fig. There's not. It's 1.00. And yeah, 3 sig figs should win. So what's my final? 225. And have you guys noticed the answers are on that paper? Look on the other side underneath 20. I'm sorry, underneath 1 through 4. Or no, sorry, 20, 24. So that gives you an option to check yourself as you go. But you'll notice is that I'm a cruel human being, and I put Celsius in the answers. So you have to backtrack to Celsius to check your answer. I'm really just making sure that you are flexible and going to count Celsius, Kelvin, and Kelvin, Celsius. But you won't put Celsius in your gas law. Okay? And hello, you made it through honors chemistry. Was it more than a quarter way through honors? I mean, AP Chem? Give me a second. I'll write you a note back to class. Yeah. All right, so go ahead, guys. Do me a favor. Go to my website and go under Unit 5. I want you to play for a while. Play is good, but this play is special. You're going to look at a simulation, and there are questions that go with the simulation. You guys have 20 minutes. You'll get 20 minutes today, 20 minutes tomorrow. It is due tomorrow. It's not due tomorrow, like morning. Like, we're going to finish in class tomorrow, okay? So you need to get a good jump on it today. I would definitely recommend sitting with a friend so that you can see the simulation on one screen and look at the other worksheet on the other screen. I think that's pretty helpful.
Did you pass out another
Not today, but I did say it.
That's not really
Did you raise it off?
Wait, do we need table with it? Gas law simulation.
Yes. Yeah, you can feel free to move, but please stay on task. Yeah. Alright, give me a thumbs up if you've made it to the simulation. It is a Java-based simulation, so yes, you have to say allow, and then you say update later, don't update, because you can update, you don't have return power. And there's a worksheet that goes along with it.
Oh, right. No, I didn't want to.
What?
I didn't bring my hard
So I think everyone's gotten to the point where they're looking at the simulation. Look up here really fast for me. Some of you guys are on part 1 and it's a little tricky. You're like, what do you mean by arrows? This is what I mean by arrows. Eyes up here. It says, so basically things are moving fast. We can't really draw them moving fast. We draw a long arrow or a long vector on them to say their velocity is fast, they're speedy. And you put a little bitty arrow on it if it's moving slowly. Does that help with number 1? Okay, if you don't want to start on step 1, that's absolutely fine. You can start on step 3, I think, which is boil off. You can start anywhere you want to, wherever's comfortable. Or you'll just finish it tomorrow in class.
Oh, wait.
I want you to go to the conversation piece, but also want you to write Yeah, I don't know people. I guess people in other classes that like partner works like you write one thing. No.